Ready to dive into some serious space exploration. We're talking about interstellar precursor missions, the kind that push the boundaries within our solar system, kind of like paving the way for going beyond.
Yeah, it's all about making those long hauls through space, well, a lot shorter.
We've got two sources for today's deep dive. First up, excerpts from a scientific paper presented at the International Astronautical Congress, and then we've got an article covering that same paper.
The really cool part, we're talking Pluto in just over 4 years, or even hitting the solar gravitational lens, that's 550 AU away, in just 13 years.
Okay, gotta admit, those numbers are kind of mind-blowing,
Yeah.
especially compared to what we can do today.
Seriously, it's a game changer.
Think about New Horizons, almost a decade to reach Pluto. So what's the secret sauce? Both our sources are pointing to advanced electric propulsion systems, or as some folks call them, ion drives.
Yeah, you might have heard about ion drives. They're already out there. But the research, it's hinting at a revolution in how efficient, how powerful they can get.
It's like ion drives on steroids, right?
Exactly. Instead of burning fuel like those old school rockets, they use electricity to accelerate ions, creates thrust, and the key to understanding their power, specific impulse, or ISP.
Okay, is specific impulse. Sounds a bit technical. Got to break that down for us.
Think of it like miles per gallon, but for a spacecraft. The higher the ISP, the more efficiently it uses its fuel, meaning it can travel farther, faster on the same tank.
So it's all about efficiency, squeezing every ounce of performance out of that fuel.
Exactly. So to hit Pluto in a few years, or that solar gravitational lens in a little over a decade, we need ISP way higher than what we have now.
Okay, makes sense. Higher ISP, faster travel times. So how do we get there? What's the roadmap for these super efficient ion drives?
The paper, it lays out 3 key things for an ideal ion drive, and it all starts with the power plant. These drives, they're hungry for power, especially for these long hauls.
All right, so what kind of juice are we talking here? Give us the numbers.
We're aiming for a power plant that can pump out 1 kilowatts per kilogram of weight.
Whoa, 1 kilowatt per kilogram. Isn't that a massive jump from what we have now?
Huge! Think about it. Current ion drive power sources, they're closer to 10 W per kilogram. Even the cutting edge stuff, nuclear electric propulsion, it's only around 100 W per kilogram. Big gap to bridge.
So where do we even begin to find a power source that powerful and light enough for a spacecraft?
$1 million question, right? The paper throws out an idea. Beam-powered propulsion. Basically beaming energy into the spacecraft from somewhere else, like constant concentrated sunlight, even when it's far from the sun.
Sounds like something straight out of Star Trek. But okay, let's say we figure out the power plant, at least in theory. What's next on the lid for this ideal ion drive?
Next up, thrust efficiency. Making sure all that power from the power plant actually turns into, pushing the spacecraft forward. The paper's goal, a whopping 97% efficiency.
97%? That sounds seriously tough to achieve.
It is. You might be thinking, well, we're already at like 75, 80% efficient. What's a few percent? But when you're talking about billions of kilometers, those tiny improvements, they mean massive fuel savings and faster travel.
Every little bit counts when you're playing on that cosmic scale.
Exactly. And to get to that 97%, we're talking about minimizing energy loss inside the thruster itself, using magnetic fields to contain plasma so it doesn't touch the thruster walls and waste energy as heat.
So it's not just brute force power, it's finesse too.
Exactly.
Okay, so power plant, check. Efficiency, check. Now let's circle back to specific impulse, that ISP you mentioned. What kind of numbers are we looking at for our ideal ion drive?
Well, the paper explores a range of values from 34,000 to 76,000 a second.
Wait, those are some serious miles per gallon numbers.
Remember that analogy? Yeah, higher ISP means way more mileage from the same propellant.
But those numbers, they're mind-blowing. Is that even possible with what we have now?
Funny thing is, the paper says the tech for highest thrusters, it's already here, or at least within reach. The real bottleneck, that super powerful power plant we talked about, that's what's holding us back.
It's like having a rocket engine that could get you to Mars in a week, but no fuel tank big enough, right?
There you go. And that's why this paper, it zeroes in on power generation as the key for the future. Solve that, and the doors to interstellar precursor missions, they swing wide open.
Right, my brain's definitely in overdrive now. We've got the blueprints for these incredible ion drives, but the power source, that's the missing link. So let's talk missions. What could we actually do with this tech once we crack that power problem? What are we aiming for here?
The paper dives into 3 specific scenarios, all within our solar system, missions we could pull off in the, not too distant future.
All right, lay it on us. What's the first mission on the list?
First up, a round trip to Jupiter. 180-day stay at the gas giant. Think of it as a quick visit, do some science, maybe snap some pics.
A quick visit to Jupiter, huh?
Well, quick is relative, right? Even with our ideal ion drive, we're still talking about 2.8 years. But that's way better than the 7 years or more it takes now.
2.8 years is still a long time to be away from home. But yeah, compared to 7, it does sound a lot quicker. Okay, what's next on the mission list?
Next, rendezvous with Pluto, that dwarf planet that used to be the 9th planet, you know?
Pluto. Even though it's not a full-fledged planet anymore, it still holds a special place in a lot of people's hearts. How long would our ideal ion drive take to get us there?
Just over 4 years.
4 years. That's incredible.
And get this, current proposals, like the Persephone proposal, they're using nuclear electric propulsion and estimate a travel time of 27.6 years.
4 years versus 27.6. Okay, that really puts things in perspective. But let's be real. The mission everyone's really buzzing about is that solar gravitational lens, right? The one that could help us find, well, maybe even life beyond our solar system.
You got it. The Solar Gravitational Lens mission, that's the holy grail of these interstellar precursor missions. It's the ultimate test for advanced electric propulsion, and the discoveries we could make, well, they're groundbreaking.
So how long are we talking with our souped-up ion drive?
Just 13 years to reach the solar gravitational lens, and get this, we could carry a payload of almost 18,000 kilograms.
Hold on, let me process that. We're talking about sending something heavier than the Hubble Space Telescope to a spot 82 billion kilometers away and doing it in just 13 years. Am I getting that right?
You got it. It really highlights what this tech can do. But remember, it all comes down to building that ideal ion drive. And that means tackling those challenges, especially that pesky power plant issue. This paper, it's a roadmap, a guide for the future.
Okay, I'm fully on board now. Blueprints for these amazing ion drives. But the power source, that's the missing puzzle piece. So tell me more about this solar gravitational lens mission. What is it about this location that has scientists so fired up? What's the big deal?
Imagine a massive magnifying glass in space. So big it can bend and focus light from crazy far away, making things look brighter, clearer.
Wait, the sun is a giant lens. I thought only black holes could pull that off.
It might sound wild, but it's true. Einstein's theory of general relativity, it tells us that massive objects, they warp space-time around them. And that warping, it bends light, just like a lens. The sun's gravity, it's strong enough to do that.
So we can use the sun's gravity to basically zoom in on distant stars and galaxies, like a cosmic telescope.
Exactly. The implications are huge. We could see things beyond the reach of even our most powerful telescopes. We could see distant objects with incredible detail, maybe even reveal planets around other stars.
Not just see the planets are there. Right. Yeah, we're talking about seeing surface details, maybe continents, oceans, who knows, maybe even signs of life.
You got it. That's why this solar gravitational lens is such a game changer. It could rewrite our understanding of the universe and our place in it.
This is where it all comes together, right? These advanced electric propulsion systems, that ideal ion drive, they could be the key to unlocking these incredible discoveries.
Absolutely. But even with advanced propulsion, reaching the solar gravitational lens, it's still a massive challenge and needs not just breakthroughs, but a long-term commitment to space exploration.
Well, I'm sold. This has been a whirlwind of information. We've gone from ion drives to the possibility of seeing alien worlds with the help of our own sun.
It is pretty mind-blowing.
This deep dive has definitely left me wanting more, especially about that solar gravitational lens mission.
And you know what? In the next part, we'll get into the nitty-gritty of a mission to the solar gravitational lens, instruments, data, potential discoveries, the whole shebang.
Can't wait. Stay tuned, folks, because things are about to get even more interesting. See you in part 2.
Back again for more on interstellar precursor missions. Last time, we left you with that image of using the solar gravitational lens to see details on distant planets, maybe even, hints of life. It's a big undertaking, makes you think about the big picture of space exploration.
Yeah, what are we really aiming for? What should be at the top of the list? It's something scientists and engineers are always wrestling with. Should we go all out with massive payloads, all the fancy tech? Or should speed be king, getting there fast, even if it means, leaving some gadgets behind?
It's tough, no easy answers. Each thing, payload, speed, they come with their own baggage. Prioritize payload, sure, you get more sophisticated instruments, but that usually means more travel time. It's like packing for a camping trip, right?
Yeah, more gear, more prepared, but heavier backpack, slower going.
Spacecraft, same deal.
Totally. Been there with that overpacked suitcase feeling. So for that solar gravitational lens mission, bigger payload, maybe more powerful telescopes, super sensitive detectors, even a little rover to check out a distant world up close. But then We're waiting longer for those big discoveries.
Exactly. But flip side, if speed is king, got to focus on those ion drives, max out that ISP.
Miles per gallon for spacecraft.
You got it. Higher ISP, more efficient fuel use, faster speeds. But that means a monster power plant. And remember from last time, that's a big hurdle.
There's that trade-off again. We zoom to the solar gravitational lens in record time, but maybe with a smaller probe, less equipment, so maybe we miss some crucial data. It's a balancing act.
It is. Comes down to what are we trying to learn and what's holding us back tech-wise. Just getting there fast, maybe a smaller payload's fine, but complex science. I got to bring the right tools, even if it means a longer wait. And then there's tech advancements. That's not really a trade-off, more like a must-have.
Right. Even if we want the biggest payload or the fastest trip, we're still stuck with where our tech is at.
Like having a killer recipe, but missing ingredients.
Perfect analogy.
And that missing ingredient, power generation. Remember those 3 keys for the ideal ion drive. Power plant, that's where the gap between now and what we need for these missions is huge.
Orders of magnitude, right? Like night and day difference.
Exactly. We need a power source that's not just crazy strong, but also feather light and efficient for a spacecraft.
So, crack the power problem, we could unlock both higher ISP and bigger payloads. More options when we're designing missions.
Exactly. And it's not just raw power either. It's got to be lightweight, reliable, working for decades in the harshness of space.
That's asking a lot, but that's what's so cool about space exploration, pushing the limits. And these breakthroughs, they don't just stay in space, right?
Totally. A power generation breakthrough for space could mean huge things for energy, transportation, all kinds of fields here on Earth. Investing in space, it's not just about what's out there, it's about making life better down here too.
Okay, trade-offs, challenges, we covered it. But now back to that solar gravitational lens mission. Itching to know more. Walk us through it. What would it actually look like? What instruments, what data are we after?
Picture this. A whole fleet of spacecraft at the solar gravitational lens working together. It's a complex dance, but let's break it down. Primary spacecraft at the focal point of the lens. It's our main observatory.
Giant space telescope, but using the sun's gravity instead of a mirror. Right?
Exactly. And to make the most of it, we need some serious instruments.
This is where it gets good. Give me the details.
First, ultra-high-resolution telescopes. Way more detailed than anything we have now. Earth-based or space-based. Think seeing a dime on the moon kind of detail.
Zoom level. Expert.
We need spectrometers, too, crucial for breaking down light from distant objects, telling us what they're made of, stars, planets, even their atmospheres.
So we could sniff out oxygen, water vapor, maybe even those biosignatures, the hints of life.
Precisely. And for that, we need coronagraphs. They block out the glare from a star so we can see fainter stuff around it, planets. Imagine blocking car headlights to see fireflies.
Perfect visual. Coronagraphs block the sun's glare so we can see those faint stars and planets. What else is on this spacecraft?
Communication. Gotta be all that data back to Earth, right? A laser communication system sending massive amounts of data over billions of kilometers.
Interstellar IMAX, coming to a planet near you.
Exactly. But let's not forget those other missions, Jupiter, Pluto. They might not be as flashy as the solar gravitational lens, but they're crucial stepping stones for deep space.
Totally agree. Testing new tech, getting comfortable operating way out there, learning about our own backyard. Jupiter and Pluto, they've got their own stories to tell.
They do. So let's dive in. Jupiter round trip, what's the science agenda? What are we trying to figure out?
Good question.
Jupiter, it's a gas giant, king of our solar system, and those moons, some of them might have the right stuff for life.
Ah, those icy moons with their hidden oceans, Europa, Enceladus, always top contenders for alien life. What will we be looking for specifically?
This mission, it's a chance to really study those moons. Signs of hydrothermal vents, organic molecules, those biosignatures, you mentioned them.
And I bet there's a lot to learn about Jupiter itself.
Tons. That atmosphere, it's a wild mix of gases and storms, that great red spot raging for centuries, learning about atmospheres and weather patterns. Jupiter's a goldmine. And that magnetic field, the strongest in the solar system.
Creates that huge magnetosphere stretching way out. A mission could study that. How it interacts with the solar wind, protects Jupiter's atmosphere.
Exactly. So much to learn about Jupiter, from those swirling storms to its fascinating moons. It's always teaching us something new.
Icy moons with potential for life, crazy storms, powerful magnetic field. Jupiter sounds like a scientist's playground.
It is. Now, let's hop over to Pluto, that dwarf planet that everyone loves. New Horizons in 2015 gave us our first real look, and it was way more complex than we thought.
I remember those first images, like a whole new world, so exciting. What would a dedicated mission to Pluto focus on?
Building on what New Horizons started, studying the surface, the atmosphere, really digging deep, looking for geological activity, past or present. New Horizons, it showed mountains, glaciers, even potential cryovolcanoes, volcanoes that erupt ice.
That's so cool.
Mhm.
So understanding how these icy worlds work, what shapes them, and Pluto's moons, can't forget about them.
Right. 5 known moons, all sorts of interesting features. Charon, the biggest one, so big. Some think it's more of a binary system with Pluto, not just a planet and moon.
Like a cosmic dance orbiting each other.
Exactly. A Pluto mission could study that, see how it formed and changed over time. Helps us understand planetary systems better.
Surface geology, atmosphere, moon system, plenty to keep those scientists busy.
Plenty. These missions to Jupiter and Pluto, they're not just about testing tech, they're about pushing the limits of what we know.
Not just practice runs, but real science happening.
Exactly. And while they're awesome on their own, they're also prepped for something even bigger.
Interstellar travel.
The real deal, going beyond our solar system.
You got it. Think about it. These precursor missions, they operate way beyond Earth's help. We got to build spacecraft that can last for decades without a tune-up or supplies.
So everything's going to be top-notch, propulsion, power, life support, radiation shielding, super resilient, totally self-sufficient.
Right. And communication, can't forget that. Sending data back from crazy distances, high quality, lots of it. Imagine sending a probe to another star and waiting years for a few blurry pictures. Not very efficient.
We need like a live stream from another star system.
Exactly. And to get there, we got to tackle autonomy. Interstellar distances, they mean communication delays, controlling a spacecraft from Earth in real time. Impossible.
Spacecraft that think for themselves, making decisions, adapting, doing science without instructions from Earth.
Like robotic explorers doing their own thing, sending back their findings. Big challenge, but also super exciting.
Sending our own little Wally out there. Exactly. So long duration tech, advanced communication, autonomous spacecraft, anything else for interstellar travel.
What else could there be?
The human element. Interstellar, we're talking decades, centuries maybe. What about the people making those journeys?
Whoa, next level complexity. Not just machines, but building communities in space.
Right. Psychology, sociology, culture, ethics, it all comes into play. Choosing crews, training them, keeping them healthy, creating a community far from Earth. Philosophers, sci-fi writers, they've been thinking about this for ages. Now it's real world stuff.
Daunting and inspiring at the same time.
It is, but those challenges, they're not unbeatable. We've done the seemingly impossible before, exploring, pushing limits. And these precursor missions, they're pushing us in the right direction, testing new tech, gathering data, showing us what's possible, inspiring future generations.
So where do we go from here? Payload versus speed, tech advancements, we covered it. Amazing discoveries at Jupiter, Pluto, that solar gravitational lens, we imagined it. Even sending humans on these epic journeys, we thought about it. Now over to you, the listener. What are your takeaways? What questions are you left with?
Maybe you're thinking about the ethics of sending people on these multi-generational voyages, or the chance of finding life on those icy moons.
Whatever's on your mind, dive in, do some research, share your thoughts. We're all in this cosmic adventure together.
And as we wrap up this part, one last thought. We talked about using the solar gravitational lens to see distant worlds, but what if we used it to talk to other civilizations across the stars?
Whoa, the sun as a giant cosmic antenna, sending messages, listening for replies.
That's what we'll explore next time, the mind-blowing world of interstellar communication. Until then, keep looking up.
Welcome back for the final leg of our journey into interstellar precursor missions. We've covered a lot of ground, from those souped-up ion drives to potential discoveries at Jupiter, Pluto, and of course that mind-blowing solar gravitational lens.
And we left you with a real head-scratcher, remember? What if we could use that solar gravitational lens not just to peek at distant worlds, but to actually chat with other civilizations across all that space?
It does sound like something straight out of sci-fi, doesn't it?
Yeah.
Using our sun as a giant cosmic antenna.
But the more you think about it, the more it kind of makes sense. At least the science seems to check out.
All right, so walk us through it. How does this sun as an antenna thing actually work?
It's the same idea as using the lens for observations, but instead of focusing light from a distant star, we'd focus a powerful beam, something like a laser, toward the lens. The sun's gravity, it does its thing, bends and amplifies that beam, sending it out across the vastness of space with incredible focus and intensity.
So instead of just catching faint whispers from the stars, we're shouting out loud and clear with a focused message. But wouldn't that take a crazy amount of energy? I mean, sending a signal across those distances, it's got to be mind-boggling.
Oh, it would be a massive energy investment for sure. But think about it, a civilization that's building and launching interstellar spacecraft, they've probably figured out energy on a scale we can't even imagine.
Good point. It's easy to get stuck in our current tech limitations,
Yeah.
forgetting that what seems impossible now might be child's play someday.
Exactly.
Okay, so let's just say for a moment we've cracked the energy problem. What do we say? Who do we even send this message to? Those are some big questions.
Those are the questions that really make you think about what it means to be human. The message itself, it depends on what we're trying to do. Just a cosmic, hey, is anyone out there? Or maybe share something about us, our history, culture, maybe even our science. Or ask questions, see if we can start a conversation.
It's like creating a time capsule for the entire human race, but on a cosmic scale. What do you pack for that?
It's a huge responsibility, no doubt. And then who do you send it to? Specific star systems where we think there might be habitable planets? Or do you just broadcast it everywhere, hoping someone picks it up?
It's like shouting into a dark forest, no idea if anyone's listening, or if you even want them to be.
Right. But even if we never get a reply, even if that message just travels forever, just sending it, that says something, doesn't it?
It does. It says we're not alone, at least in spirit. That we're curious, hopeful, wanting to connect, even across those incredible distances.
Exactly.
Okay, you've convinced me. The solar gravitational lens is a giant cosmic messenger. It's captured my imagination. But let's get practical for a second. What would this system actually look like? How do you even build something like that?
Well, like most complex missions in space, it would involve a team of spacecraft, all working together. One spacecraft, maybe orbiting the sun, acts as the transmitter, sending out that powerful beam.
And then another spacecraft at just the right spot, that focal point of the lens to catch any replies, right?
Right. But that receiver, it needs to be incredibly sensitive, picking up whispers from light years away. Imagine trying to hear a whisper in a hurricane.
And then deciphering those messages. What if it's in a language we don't understand? What if it uses tech we haven't even dreamed up yet?
Another layer of complexity for sure. Like translating ancient texts from a lost civilization, but on a cosmic scale. We'd need linguists, anthropologists, scientists, engineers, everyone working together just to get started.
This is getting pretty mind-blowing, I gotta admit. But exciting too, right?
It is. We're on the edge of something big here, something that could change how we see ourselves, our place in the universe.
Definitely a lot to think about. But for now, let's bring it back down to Earth. We've talked about those ambitious missions to Jupiter and Pluto, that incredible solar gravitational lens, and we've even explored this mind-bending idea of using our sun to chat with other civilizations, goals that seemed like pure sci-fi just a little while ago.
And here we are talking about them like they're just around the corner.
Yeah.
It shows you how fast things are changing, how much we're learning about the universe.
Absolutely. So, as we wrap up this deep dive, one final thought.
Yeah.
What role will you play in all of this? Will you be the scientist designing those spacecraft, the engineer building them, the explorer venturing out into the unknown? Or will you be one of the many people back on Earth who supports this incredible endeavor, cheering on the pioneers, celebrating their discoveries?
Whatever path you choose, remember, the future of space exploration is in our hands. Dream big. Push those boundaries. Keep that spirit of exploration alive for yourself and for generations to come.
And that's a wrap on our deep dive into interstellar precursor missions. We've traveled from the nuts and bolts of ion drives to the mind-blowing possibilities of communicating with other civilizations. It's been an incredible journey, and we hope you've enjoyed it as much as we have. Until next time, keep looking up.